Okay, so let me share screen and we'll do kind of a little introduction to what regression is. All right, so this is the, once you get to week 3, this is the full-blown worksheet that you won't get to till like week 4, so don't be confused. How the author does it is he starts you off with baby steps. So one of the Excel things is going to be 1, the Excel app 1 for this section, and it's just going to work you through 1A, 1B, 1C, 1D. And then the next one will be 2, but what he does is he keeps adding them on so we can reference back to it. So it kind of all ties back together. Just going to speak from the kind of the master sheet here. All right. So we've kind of seen data before, but let me just introduce you to what a data set looks like that you'll be dealing with your paper. So this particular data set is in your book, by the way. So it's part of the book material in chapter 5. These are number of observations, which I think is just 30, if I remember right. Yeah, so 30 observations on pizza. We've got quantity of slices, the price of a slice, tuition at a college town, and the price of soft drinks, so a related good. And then whether that town is located in an urban area and whether there's residential neighborhood around it. So that's kind of our setting. So we're gathering data from college towns and trying to think about the demand for pizza, estimating the demand for pizza. And tuition, what do you think that is? So this is the price of tuition. What do you think that variable is trying to capture in terms of a demand analysis? And think about, we're gathering data from multiple college towns. So one might be Manhattan, one might be Lawrence, one might be Ottawa, one might be South Bend, Indiana for Notre Dame, one might be Yale, one might be, so all of those 30 observations are different college towns. What might the tuition variable, so the price of tuition, what might that be capturing? The wealth, yeah, and income, probably more specifically. So higher tuition, the students who are going to high tuition schools probably tend to have higher incomes. So in terms of our estimation of demand, we've got price, of course. Price is inversely related, the price of pizza, quantity of pizza. And then income, of course, is one of our other variables. A lot of times in empirical analysis, we might not have income. You guys might find this in some of your studies that there's a variable that I really like to have, but I don't have it. And so we're going to use tuition as a proxy for income, right? Because those two things should be correlated together, maybe not perfectly correlated, but hopefully give us an indication of income. Towns with higher college towns with higher tuitions might mean higher income kids going to those colleges. Again, it's not a perfect measure, but if we don't have income, as an empirical researcher, we want to include an income variable. So it's probably more important to include a not so perfect variable that captures that thing that economic theory tells us is important, right? To the purchases of pizza, what kind of income are you making? You make more income, you buy more pizza. We want to capture the sensitivity of that income variable to the purchases. And then soft drinks, does it matter or not? Yes, we say that they're what? Complements or substitutes? Price of soft drink and quantity of pizza. Complements, right? So if the price of soda goes up, and I always drink soda and pizza together, then the bundle goes up in price, causing me to maybe buy less. So does that price variable end up giving us a negative sign or positive sign after we crunch the data? The idea would be soft drinks get more expensive and I buy less pizza because the two goods are complements of each other. Again, economic theory tells us that there'd be a negative relationship. Does that bear out empirically? And more importantly, we can, with this type of analysis, look at the sensitivity of that variable quantity of pizza purchased compared to the soft drink And we might be able to advise our client that, hey, if you raise soda prices by 20 cents, you're only going to lose a little bit of pizza because they're not very sensitive with each other. People are still going to keep coming in. And so this is a good way to make some money, right? And then what do we see? What do you pay at Applebee's or at a pizza place for your fountain soda drink? What do you guys pay when you go out to eat? What do those usually run? Just a glass of maybe bottomless cup of soda. $2.50, $2.30, right? So over $2. What do you think the cost is of that at the margin? 15 cents something, right? And so they get people, that ends up being a nice profit center. So we use this type of analysis to help provide information to businesses on what the proper pricing is in order to maximize profits. And so that's why we see those soda prices. Another classic example is the movie theater course, right? So the movie theater jacks up the price of soda and popcorn, even if the ticket to get in is only a couple bucks, although those are going up. I went out to a movie for the first time up in Lawrence, ever first time, but they just got the new seats in. You guys ever go up to Lawrence for a movie? And they got the big recliner seats. And we went for the regular primetime show. It was 8 o'clock in the evening or something. And so it was $11. I was like, way up there back in the day. My wife and I used to have our weekly date night at the movie theater, but it was the dollar theater. And so we were almost guilted into buying popcorn when you're only paying $1 to get in. Okay, so this sheet will ultimately bring us to doing a statistical analysis. I'm not going to do that today with us. I just kind of want to get our feet wet with what does regression do. Okay, so here are these data points. So we took that 30 observations, and we've got the price per slice and slices per month. So one thing to note, quantity on the vertical axis, price on the horizontal. Sometimes we do stuff like that because either A, Excel doesn't want to play nice with it, and maybe we just don't want to fart around with it. But if you go way back to math class, the vertical axis, the y variable, was usually the dependent variable, right? So this is the way it was kind of meant to be mathematically. But Alfred Marshall, who more or less invented the demand curve, when he originally graphed it, put quantity down here and price up here, and it kind of stuck ever since. But mathematically, we don't necessarily do it that way. And doing it this way kind of helps with our format. And so what regression does is takes a straight line and comes up with the best fit. So one of the exercises that this is going to do is to say, how could this negative relationship, what does that demand curve look like? There's my data. Well, that doesn't seem quite right, right? So let me see if I can do this here. A little bit more slope, maybe. So you can kind of fit this line. This is what regression analysis is. When we let the computer work for us, it's doing what I'm doing right now. It's kind of trying to find, like, where is the best fit given the data? Where is the best fit? And I think maybe it'd be even a little bit, so this is kind of the good old-fashioned eyeball trick. And so maybe there, I don't know, maybe here. So you can kind of play around with it. But this is the process that the computer's going to go through. So there, I'm starting to be happy right there, right? So we got kind of a balance of the line fitting through that data point. So the process that the computer goes through is called ordinary least squares. Or OLS is the statistical process, also known as regression, basic linear regression. And what it's doing through a computer algorithm, it's going to take the sum of all the error terms. So now we call this error. Once I get this in there, like from here to here is how much it was off. right? The error that was involved between here and here, this vertical distance, that 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 vertical distance. And so it's going to minimize the sum of the least squares. We're going to square the error because we don't really care if it's below the line or above the line. Above the line would be a positive error. Below the line would be a negative error. I don't really care. So mathematically, to take care of that, we square it, right? Because a negative 2 times, or negative 2 squared is a positive 4, right? Then we're going to add up all of those errors, and we're going to keep wiggling this line around. We're going to keep wiggling it around until the sum of the least squares is the smallest possible. And that's how the computer goes about fitting this into this space. Okay, questions on that? Conceptually, you got what the computer's doing? Our eyeball thing is kind of the same thing, but the computer's going through a formula to do that same part. Now, what we have is this red line has a nice slope-intercept form. So we're back to, oh, I forgot my markers. Okay, I think we'll just live without markers today. So it kind of hurts me a little bit. I don't even think about that. So y equals mx plus b, right? So slope-intercept form. So y-intercept is q. So really we're in q equals slope times the price per slice plus the intercept. Oh, you got one. Awesome. I mean, I could do my sprint down the stairs for this, but I don't think I'm going to do a ton of work with it today. All right, so I'll make sure we're not. This is dry erase. Okay. So slope-intercept form. And sometimes we put the b first or whatever. So we've got the intercept and the slope. So there's your slope term, and there's your intercept. And so for the demand equation, you might remember from intermediate micro class, this was the inverse, or this is the demand equation. The inverse demand equation was when we put the p over here. But so this is q equals the slope times the price of a slice plus the intercept. And now we have it. So I've got about a 19.5, and then whatever my rise over run turns out to be, right? And so what this helps us do now is if I increase the price of a slice $1, how many slices am I going to lose? So if I increase the price, now remember it's kind of weird going here because I got quantity on the vertical axis. So increasing the price of a slice, if I'm currently, look at, I happen to run right through this point. So let's say that is our college town, right? That's exactly where we are. If I increase the price of a slice, how many slices am I going to lose? Just simple rise over run. All right, questions there? All right, so let's see, that is, what am I on, the PQ? All right, so this is the data. After you run regression in Excel, it cranks out some output for you. And so the author has kind of ran through what this one turns out. He ran it for you. He ran the computer, and then you guys will end up verifying this later. But here is the parts that I was just talking about. So the coefficient is the slope term. So the slope term was negative 0.08. So we got a negative sign, so that's good. So sometimes we don't necessarily graph it out, and we know that it's going to be negative. We just let the computer do it. Got the negative sign. So that's a good start to my empirical research paper. That my empirical results matched what I predicted in theory. And then we have an intercept of 20. So even from my eyeball test, this is the actual one, we can kind of see how that did with my eyeball test. So my eyeball was a little off. That's why we economists don't trust the eyeball, right? Looked like it was more like that. And So we've got our 0.085, and so we were measuring it in terms of cents, right? So if our slope term is 0.085, let's call it, for the price of a slice, who can give me an interpretation of that? What's it predicting in terms of our demand? So we've got slices per month, and we got price per slice in cents. So who can give me an interpretation of the coefficient 0.085? There's a couple different ways to do it. We did lots of interpretations of this. This reminds me of, what was that, spatial class? Remember I kind of hammered you guys on that? This is the same thing. I'm going to go to the random number generator. Kaylee, number between 7 and 13. 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Tyler. So we've got quantity of slices, which is quantity of slices per month, remember. So this is per month. And then this is the price of a slice in cents. So there's 100 cents per dollar. So you could do an interpretation in terms of cents. So imagine if I increase the price by some amount. Walk me through what that interpretation is. Let me give you one little nudge. How about a 1 cent increase in the price of slice will, let me complete that sentence. A 1 cent increase will lead I like it so far. Will lead to. Now remember, this is an equation, right? So I'm bumping this up by 1, and then this result is changing. An increase in quantity of slices, but now you can tell me how much of an increase. If this increases by 1, what would it increase by?
You said just by 1.
Yeah. So the price is going to increase by a penny. A 1 penny increase in price will lead to a be brave. It's okay if you're wrong. And it's probably just staring you in the face. I have a feeling you've gotten it, but. So this is going to go +1, right? So imagine this thing going +1. If this goes up by 1 and everything else stays the same, whatever, this was like 20, right? But this goes up by 1, what's going to happen to the quantity of slices? And it's this times this. And you're right, by the way, will lead to a something I heard you say the change in quantity of slices. Let me take you a different one. Tyler, because I really want this to hammer home for everybody for that matter. If the price is $1 currently, right, $1, how many slices am I selling per month? If this intercept is 20. So if the price of a slice is currently $1, which is 100 cents, by the way, right? How many slices am I selling? Now I've got 0.085 times 100 plus 20 equals, what do I got here? 20 plus, what is this thing? Shifting this over a couple decimal places, right? Times 100. So I get 28.5. So I'm selling 28 slices per month. Now, my question is, if I bump the price up to 101, increase it by 1, how many more slices am I going to not sell? I guess if I'm increasing the price, I'm going to decrease quantity. Yeah. So we've got the change of how much. So to complete the statement, a 1 cent increase in the price of slice will lead to a point. Where you get the 0.1 from?
You just said 1.1.
Yeah, so my new number, from this statement, this is going to become 101. So how much is this going up by? Or down by, I guess. Sorry, this is really a negative number here. That's negative slope. 0.085, right? So we could do the math out here again, but really all we're changing is 1. So it's 0.085. So this is going to go minus 0.085. And my new number is going to be still 28.42, right? 42 something, whatever, 415. Do you see that now? Any questions? All right, so this is measuring the sensitivity. So a 1 cent increase in the price of slices will lead to a 0.085 decrease in quantity of slice. That's it. So that is our estimation. That is our estimation of demand. Okay, cool on that? So, let me just briefly say this R-squared. This measures the how much information we're explaining through this variable, or through the, actually it's through the whole regression. We only have the one variable in here now. So the interpretation of this would be 50% of the variation in the quantity of slices is being explained by the price of slices. 50% of the variation in the quantity of slices per month is being explained by the price of slices. Right? So that's our R-squared, which is something, well, again, you're not supposed to, I am meaning this to be an overview. You're going to go through all this later, but that's, I feel like I want to expose, I haven't done this with the other capstone classes, exposed you to it this early, but I kind of want to get you thinking and go on it.
So we don't have to answer anything for this one. It doesn't answer your question.
No, not yet. This one doesn't have it. Yep, you're just kind of learning the lingo at this point. So some of the other data that it shows, notice the number of observations is shown up here. Standard deviation and standard error of the coefficients. So one of the things we wonder is this significantly different from 0? Eyeballing it, you're kind of like, well, that could be 0, right? So is there 0.085 is kind of a small number. So part of our empirical analysis wants to question, is price of slice really explaining anything? Or if I gathered some other data, would this be maybe 0 or positive or whatever, insignificant? So we have a test for that through the standard error and then what will be known as the T statistic. So you might remember this. This is just to kind of give you a conceptual overrun of this again. The bell curve. Remember the bell curve? We talked about it a few times in class. So this is the normal distribution for a variable. The normal distribution. And what we're wondering is, can we be pretty confident that this number's solid? And so we go through a statistical test called the Tstat to see if it is. Long story short, if this number is bigger than 2 in absolute value, so -2, 2, doesn't matter. If this number is bigger than 2, then it is statistically significant. In other words, this number is a good number. It's significantly different from 0. In other words, price of slices math is what we're trying to do with significance. And furthermore, this coefficient of 0.085 does convey some meaningful information. If this T statistic was less than 2, then we'd say it does not pass the test. This is equivalent to 0. I don't have enough credibility with the number that it's different from 0. And then we'd say, sorry, price of slices and quantity of slices, they're unrelated to each other. The computer's going to always crank out a number, but the significance of that number may not be there. And so that's called the Tstat. Okay, questions on that? Did you guys remember that at all from previous statistics class? Did you do a little Tstat? And then p-value and the 95% confidence intervals. All right. This kind of says what I just said in probably nicer language. So this talks about the R-square. And then this talks about the process that I told you with the sum of least squares, fitting that line. This is going through all the details of the error terms and how that was calculated. So this will walk you through all of that. The intercept is here, so this is all just giving you kind of the rundown of what I just gave you. And then this last thing is calculation of the error terms, just to kind of prove the process to you. So this is a little exercise that he runs through to show how that number was actually calculated. That's it. We'll call it a day there. Welcome to Regression.